Well, I've got an opening question for you here, a little different. See if this is on the screen here. Suppose a bear walks 90 feet south, then 90 feet west, and then 90 feet north. To end where it started. So it walks south, west, and north, but still managed to get back where it started somehow. What color is the bear? Oh, you've heard it before. Very good. All right. This is actually a math question, right? If you figure it out. How can a bear walk 3/4 of a square? Well, it walks 90 feet south from the North Pole, 90 feet west from the North Pole around a line of constant latitude, and then 90 feet back north, and it gets back where it started. Only from the North Pole can you do that, so it must be a polar bear, right? A white bear. Anyway, so there's that one. That one must be too common, huh? All right, well, today we want to do calculus with parametric curves. Last time we introduced parametric curves, sometimes I think we just need to say this is how you define curves in general. What is a curve? You always hear about curves. Well, a curve is something you can write out parametrically like this with x of t and y of t continuous is what a curve really is. So we'll recall that a curve given parametrically, you can give it other ways too, but it's something you can write parametrically. Is a mapping c of t that gives a bunch of coordinates x of t, y of t in the plane, right? And we said this is even more important in 3 dimensions, but for us, we're just going to do it in 2 dimensions. With x and y continuous functions, and t in some interval of real numbers. Now, that'll be a curve. And in here, t is called the parameter. And it's sort of a dummy because what you're interested in is this mapping from the real number line into curves in the plane. And you could use tau or whatever your favorite letter is. Now, one thing we said was right at the end last time, the slope of the tangent line to such a curve can be calculated, provided that the functions x of t and y of t exist. So now you need the derivative. And furthermore, you need x of t, x prime of t, not equal to 0 at t. Maybe you remember this one. Came out to be, let's see, do I have room here? Yeah. Dx dt, dy dx is the slope of the tangent line. Can be calculated as simply dy dt over dx dt, right? You have this problem if x and y are written as functions of t, how do you take the slope of the tangent dy dx when y isn't written as a function of x? You just take dy dt and divide it by dx dt. Sometimes you can eliminate the parameter and write y as a function of x. We did that in some examples last time, in which case you can take dy dx directly. But more generally, you can compute it this way. So we'll give a short example of that. Here's an important curve that's going to come up later this semester, an ellipse. Right? One of the nice things about these parametric curves is you don't have to just deal with functions. Suppose I took the so-called ellipse, x squared over 4 squared plus y squared over 3 squared equals 1. That looks a lot like a circle if you think about it, right? How is it different from a circle? Say if I just had 4 squared here, this would be x squared plus y squared equals 4 squared, a circle of radius 4 at the origin, right? But I'm going to make the circle a little oblong. I'm going to put this over 3 squared. And so now instead of getting a nice circle, x goes between plus and minus 4. When y equals 0, x is as big as possible is equal to 4 or minus 4. And when x is 0, y can be as big as 3 or as little as minus 3 to make y squared over 3 squared equals 1. And so this goes kind of like this. And we'll do ellipses later in the semester, as I said. Goes between plus and minus 4 on the x-axis and plus and minus 3 on the y-axis. And since it looks almost like a circle equation, it just gives you kind of an oval equation that we call the ellipse. And you can move these elsewhere on the plane, but this in particular is ellipse at the origin that we say has semi-major axis 4 and semi-minor axis 3 instead of a radius, right? How can we write that parametrically? This is actually kind of an important equation because ellipses turn out to be very important functions in all sorts of neat applications. And so I thought I'd introduce this one. It's also in the chapter, even though, like I said, the book hasn't got to talk about ellipses in general yet. This can be given parametrically in an analogy to the circle. All right, what did we do for a circle if this is x squared over 4 squared plus y squared over 4 squared equals 1? Like that. How could we write it parametrically? It's x squared plus y squared equals 4 squared. Remember, if it was x squared plus y squared equals 4 squared, we could let x equal 4 cosine t and y equal 4 sine t, and let t run, say, from 0 to 2 pi, and then t was the polar angle, and it went around once on the circle of radius 4, right? It was the unit circle of trigonometry multiplied by 4, so you're 4 times as far out. And that gave us the circle of radius 4 as you went polar angle from 0 to 2 pi. Now, if I just change this to a 3, I'll sweep out the ellipse with semi-axes 4 and 3, it turns out. And that's a nice way people like to parameterize ellipses. You can see that it works since, look at what happens if I take x squared over 4 squared plus y squared over 3 squared for this parameterization. What does it give me? All right? Well, x is 4 cosine t, so this is 4 cosine t squared over 4 squared plus 3 sine t squared over 3 squared. And what's that? Well, let's see. The 4 squared here cancels this 4 squared. And the 3 squared here cancels the 3 squared here. And I get cosine squared plus sine squared, which we remember from the Pythagorean identity is 1. So sure enough, all these points in this parameterization lie on this ellipse here, right? You satisfy the same equation. It doesn't prove that it goes all the way around here. I'll wave my hands a little bit rather than try and make it the complete rigorous derivation of it is not worth it. But suffice it to say, t went from 0 to 2 pi in the circle, and now you just stretched it a little so that y is only 3/4 as big as it used to be. It still goes around in a circle. T is still going around. It's not the polar angle anymore, except when you're along the axis, but it still goes all the way around in the same kind of fashion. So this sweeps out the ellipse when you do this. And now, suppose I look at that and I say, what is the slope of the tangent line when t equals pi over 6? It's not actually the angle pi over 6 quite, but what is dy dx, the slope of the tangent line, when t is this nice easy number for calculating sine and cosine, at least pi over 6? How about that? All I have to do is use, let's call it equation 1, and say, given this in parametric form, we can now find a slope of the tangent line to ellipse, which we couldn't do before. This would be maybe over here somewhere. 4 cosine pi over 6 for sine pi over 6 would be maybe this point right here. And we're saying, what is the slope of that tangent line, I wonder, right? dy dx at that value of t. Well, it's easy, right? I'll just say dy dx at any point t along the curve is just the derivative of y. Y was 3 sine t, so its derivative is 3 cosine t. We'll say by 1. And the derivative of 4 sine t, I'm sorry, let's see, y, yeah, and the derivative of 4 cosine t would be minus 4 sine t, right? X was, well, I'm calculating dx dt down here. X was 4 cosine t, so dx dt is minus 4 sine t. And what I get is minus 3/4 cotangent t at any value of t, right? So now in particular, at t equals pi over 6, we can get the slope, right? We can get the slope at any point on the ellipse by just plugging in a number. Now, even though this wasn't a function, we didn't have to break it up into 2 pieces. We just use the parametric dy dt over dx dt, right? And I can plug in any t value I want and find the slope. But actually, at t equals pi over 6, then we get dy dx is cotangent pi over 6, right, which comes out to be times 3/4, minus 3/4. Gives us minus 3/4 times square root 3, or minus 3 square root 3 over 4. All right, remember calculating cotangent on the unit circle. You take just the x coordinate, square root 3 over 2, over the y coordinate 1/2, and you get square root 3 for the cotangent. All right, so there's that slope of that one. Any comments or questions on that one? That's part of the homework, is to be able to calculate slopes of tangent lines to curves. All right, let's get rid of this then. A second topic is calculating arc length. Okay. The arc length can be calculated along a smooth curve. Another name for smooth in this book will be continuously differentiable. I'm trying to introduce you to some terms you're going to hear in higher mathematics and in the sciences. Anybody heard the term continuously differentiable before? What does differentiable mean? Yeah, it just means it has a derivative. So differentiable means it has a derivative. Continuously differentiable means it has a continuous derivative. So derivative exists and is continuous. Sometimes they'll say 3 times continuously differentiable means it has 3 derivatives and they're all and the last one's continuous. In calculus books, sometimes, this is such a long phrase, we'll just say smooth. And smooth will mean that it has a continuous derivative. Be careful in higher mathematics. Sometimes, like in topology courses, in higher mathematics, smooth will mean as many derivatives, continuous derivatives, as you need. And in topology courses, it may even mean that it has an infinite number of derivatives, all continuous. automatically, because if it's differentiable, then it's continuous, right? But by theorem. But in higher applications, it may mean it has as many derivatives continuous as you need. But for us, it'll just mean it means one, right? Because if we have a curve that maybe it goes like this, is that continuously differentiable? It's not, right? It's got this corner. This looks like the derivative, the slope of the tangent line is changing continuously as I move along the curve. But then I get up to here, it's got that slope on one side and that slope on the other. And at that point, the derivative has a jump, right, from positive to negative, and it's not a continuous derivative. It doesn't even exist at the point, right? So this one is not continuously differentiable if it has a corner in it. And we're going to avoid those. So it meets our intuitive concept of smooth. It doesn't have any corners in it, right? And that's what most calculus books mean by smooth, is one continuous derivative. For that, we can calculate arc length as follows. Suppose we have a plane curve C given by x equals x of t, y equals y of t, both having a continuous derivative. I say, I wonder how to estimate the length of that curve. And it doesn't even have to be a function now, since it's a parametric curve, but I drew it as such here just for convenience. I could think of breaking it up in a bunch of little line segments like that, take line segments like that and say, well, the arc length is approximately the sum of the line segment length. So if with n subintervals, so t, and let's make this more, let's make t running from A to B. So that the idea is that this is the point x of A, y of A, and this is the point x of B, y of B along the curve. And at any point in the middle, oops, it's not the curve, x of t, y of t, you're at some point traveling along. And you sweep out the curve going from the point A to point B, if you like, that direction. So sometimes we'll draw an arrow on it to show what direction you're moving. You can have a curve where it goes forward and back, and also if you want, but for our purposes, suppose it goes forward. With the partition of the interval AB into n pieces, and suppose I let t0 equal A and tn equal B, and I break it up into n subintervals, x0 to x1, x1 to x2, x2 to x3, and so on up to xn minus 1 to xn. I can figure out an estimate of the length of the curve by adding up those line segments, right? The kth segment goes maybe from x of tk minus 1, y of tk minus 1, to x of tk, y of tk. So there's one of these line segments. And I know how long it is by the Pythagorean theorem, right? I can say, well, this is the difference in the x-coordinates, x of tk minus x of tk minus 1. I could also call that delta xk, the length of the kth x increment. And this could be y of tk minus y of tk minus 1, and also called it delta yk, is the kth increment in y along one of these little line segments here. And so this side of the triangle, I could call it delta sk, the kth approximating length here, and I would say by the Pythagorean theorem, it's the square root of delta xk squared the bottom length, plus delta yk squared. This notation gets real awful, right? Delta xk is one variable with two letters delta x and then incremented by k. So I mean, it's just one variable squared plus another variable squared is all that is, despite the messy notation. And so that's the length of the line segment. Now I know how to estimate the length of the curve. I just add up all line segments like that. Now, the arc length, let's say S of the whole curve, or let's use L actually. L of the curve is approximated by the lengths, sum of the lengths of the line segments by the following. We're just going to add all these lengths together, delta S1, delta S2, delta S3. Sum k equals 1 to n. There's n line segments, so I'm summing over all the line segments. Square root of delta xk squared plus delta yk squared, like that, right? Sum of the lengths of the line segments. Well, if this is actually a smooth curve, a curve that has a continuously changing derivative, it can be argued actually that in the limit, as the number of pieces goes to infinity, the error between this and what you should be calling the length of the curve goes to 0. So furthermore, if x prime of t and y prime of t are continuous, we're just going to go ahead and define, because the errors tend towards 0 in a general sense, L equal to the limit of this approximation. Let L be the limit as n goes to infinity. Sum k equals 1 to n. Square root, I'm sorry this notation is so klutzy, it takes a long time to write, delta xk squared plus delta yk squared, where these are the increments in x and y on the kth subinterval, right? Now, how is that going to ever calculate us on arc length? That looks really hard to do, doesn't it? So what I do is I appeal to some things from Calculus 1 and say this is also the limit as n goes to infinity. Can you see all right in the back? Is this big enough and high up enough? Let me know when I'm getting too low. I'm a little worried here. Limit as n goes to infinity, sum k equals 1 to n, and I'll copy this again, except I'll make a bigger square root sign, delta xk squared plus delta yk squared, and I'm going to divide the inside the square root by delta tk squared. And then multiply outside by delta tk. And so this is actually the same quantity, right? Because the delta tk outside cancels the 1 over delta tk squared inside the square root. Right? This will cancel these out and give me back here. But now something interesting is happening. I have room here. Now, some magic from Calculus 1. This one here is delta xk over delta tk squared, right? Delta xk squared over delta tk squared is delta xk over delta tk squared. But this was x of tk plus 1, which is tk plus delta tk. I'm sorry, tk minus 1 plus delta tk. That's x at tk. less x of tk minus 1. Let's write that better. All right, it was the difference, it was the x increment. And then I've got delta tk over here. And I should put what a delta tk is. Delta tk is tk less tk minus 1, right? So it's the width of the kth interval in t in the partition. So I'm just using that abbreviated notation here. And so that's what this is. And if you think about that, that has some significance in calculus 1. Like this, if you put t versus x, and maybe this is the curve x of t, right? And I go from this point here at tk minus 1 to this point here at tk. What does this represent here? tk minus tk minus 1, this is delta tk, the width of the interval. And this top part is the change in x, goes from here to here, x at tk minus x at tk minus 1 then. And so what you have here is the slope of the secant line. All right? It's the rise over the run. That's what that is. Now, there was a theorem that you probably haven't used since that we're going to need now. Didn't seem very important at the time, probably, that says when you have a function with a continuous derivative, that's what we said, we're going to posit that this is continuous derivative, then there's some point somewhere in the middle, we could call it tk star, at which the slope of the tangent line is equal to the slope of the secant line. In other words, they're parallel lines. At what point, we don't know, but it just postulates that there is, well, states that there is, it's a theorem, right? A point tk star at which this is actually equal to the derivative. I get going off the screen here, let's see. So this is actually equal to f prime at some point tk star in the kth interval. That's what it says. What theorem was that says the slope of the secant is equal to the slope of the tangent somewhere in the middle? Remember seeing that? Nobody saw that before? Okay, well, at least you're not liars, huh? Okay. That's called the mean value theorem for derivatives. Mean value theorem. There's also one for integrals, but I don't have room to write for derivatives, so I'll say mean value theorem. All right, says that this is actually equal to the derivative somewhere in the middle, which means that if I continue this up here now, that this definition that L is equal to the limit of the sum, I can replace this with the derivative at some intermediate point. So L is now the limit as n goes to infinity of the sum k equals 1 to n of the square root, and I can replace dx or delta x squared over delta t squared with dx dt squared at some intermediate point tk star. So this means plug in tk star at the intermediate point. We don't know what it is. The mean value theorem says there's just some point, and there might be more than one point where the slope is the same, but right, if the derivative changes continuously, somewhere in the middle, it goes from having slope less to having slope greater in this case. It's equal somewhere in the middle if it changes continuously. And then similarly, this one has the same thing. You write y as a function of t, and this is the derivative of y with respect to t at some other intermediate point by the mean value theorem. This way you get to see why you actually studied those things, right? If you're a math major, this is important. And we can say this is actually equal to this at some intermediate point by the mean value theorem for derivatives. I'll call this TK double star because it might be a different point than this one where the y derivative is equal to the slope of the secant line. All right, so there's what we've proved. Now, if we start with this definition, we get to this. And now what does this look like? Maybe that looks like something you've seen before. What does it remind you of? Get this. I want to remind you of something you saw in Calculus 1. Remember seeing this before? Let's see if I can get over here. Recall now, if I write the definite integral is the one with the endpoints on here, a to b. That had this definition. I need to get rid of this now. Of f of x dx. What was the definition of this definite integral? It's not antiderivative capital F at b minus capital F at a. That's the fundamental theorem of calculus that says you can do that. One part of two in the fundamental theorem of calculus says this is equal to f of b minus f of a. But what's the definition of this? Now, the fundamental theorem of calculus says you can evaluate with antiderivatives, but the definition is that this is the limit as the number of rectangles in the partition goes to infinity of the sum k equals 1 to n, 1 to n, f of xk star, where xk star is any intermediate point whatsoever, delta xk. It was that rectangle picture, right? If you had a function f of x on an interval a, b, you would break it up into subintervals x0, x1, xn, and you'd partition it, and you'd take all the rectangles, and this was right base times height. This was the base, and this was the height. Base times height plus sum of the rectangle areas. So the definite integrals was defined as sum of the rectangle areas, and it looked like this, where xk star could be any intermediate point, because in the limit it didn't matter which point you picked in the middle, you got the same value. And so that was fundamental to defining area. If you got the same value regardless, this was the definition of the definite integral. That's what this looks like. It's a function at an intermediate point tk star, a function of t, intermediate point tk star, limit sum, just like that, which means that this is actually a definite integral. This, in fact, since t goes from a to b, is the integral from a to b, just like we have here. And that our f of x is this one, or f of t, I guess I should call it. This is the function we're integrating. And the idea was you replace f of xk star with f of x, you replace delta xk with dx, you replace the limit sum with the integral sign, and this notation stands for this, right? So the notation for this is integral from a to b of the square of this function, that's the square root of dx dt squared plus dy dt squared square root. Right, and then delta, I left it. And I left it off. There was the delta tk outside. I'm sorry, I forgot to put that on. Right, outside the square root was the delta tk still. And the delta tk, just like this one becomes dx, delta tk becomes dt in the notation. So this notation means this, actually, except I've been just a little sneaky here. Technically, this is at tk star, this is at tk double star, so it's not quite the definition. There's another theorem that says even if these aren't the same, it's still equal to the definite integral. So this is almost the definition. And by theorem, it's equal to the definition of the definite integral. So we'll say by theorem, I think it might be called Lamb's theorem. I can't remember the name of whoever it's named after, but there it is. What we've shown is that definition of arc length leads to this integral. You can evaluate it as a definite integral when you take it to be the limit of the sum of the line segments. And provided the derivative of x and y are continuous, you can evaluate the arc length of the curve this way. This is formula 2. I hope it didn't take too long to derive, but I think it's worth seeing where it comes from on this. The arc length of the curve from a to b, the smooth curve, is integral from a to b of square root of dx dt squared plus dy dt squared dt. That's how we'll evaluate arc length along a curve. Now, if I didn't take too long on that and use up all the period, huh? It's real nice to see where that comes from. But what's great about this is, unlike Calculus 1, where you can maybe try and work on an arc length of a function, this can meander all over the place like this. It doesn't matter that the curve isn't a function as long as x and y are smooth functions of t along here. You can just estimate the curve the length of a curve that wanders around like that now. So let's do a simple example. Suppose I had this example here. This is actually one of the homework problems, if I can get it here. You might get different numbers on yours. They like this notation for a curve. C of t equals, and they put x of t here and y of t in the next one. 10 plus 12t, 8 plus 8t. And suppose t runs from 6 to 9. All right. Find the arc length of this curve. We don't actually need this fancy formula for this one. Why don't we need this fancy formula? So the idea is, when they write this, they mean that this is x of t, the x coordinate, and this is the y of t coordinate. And as t evolves, you get these coordinate pairs x, y moving along the curve, right? Why don't I need that formula for this one? You can recognize from last time if you're clever. Yeah, it's straight line. You use the Pythagorean theorem. Very good. Insight in these things, when it's a plus bt, c plus dt, just a number times a number plus a number, this is always a straight line. And when you go between two fixed numbers, then it's a line segment. So this is a line segment from one point to another. We could use the Pythagorean theorem and calculate it to check and say the first point, so line segment, we put in t equals 6, and this one we get 10 plus 12 times 6 is 82. And the second one, 8 plus 48, 8 times 6, right, gives us 56. And it goes from that point to, and then I plug in 9, 10 plus 108 is 118. And 9 and this one gives 72 plus 8, right, is 80. And so we just use the Pythagorean theorem that this is L equals square root of 118 minus 82 squared. There's the change in x squared, plus 80 minus 56 squared. Let's see, and I get square root of 36 plus, wait a minute, 36 squared plus 24 squared. Should come out to be 12 square root 13. Hopefully. Right. So there you can make a double check and see if we get that same number by our formula for this easy case. By equation 2, our arc length formula, we get L, the arc length, is the integral. Well, t goes from 6 to 9. Well, let's write it out. Integral from a to b, square root of dx dt squared plus dy dt squared. Okay, plus dy dt squared dt. Well, these are easy derivatives. That's why I picked the example. It's not too hard to compute. Dx dt derivative of x here is just 12. Squared plus dy dt is just derivative of 8 plus 8t is 8 squared dt. So let's see, 144 plus 64 is 208, right? So I got square root 208 that can then come out. Integral from, oh, this went from 6 to 9, sorry. 6 to 9 dt, and what you've got at 1 dt if you like. So it's square root 208 times, when you integrate 1, you get t. So this just becomes 9 minus 6 is 3 square root 208. Hopefully it comes out to be, this is 4 square root 13. So it becomes 12 square root 13, sure enough. The arc length formula gave us the value we expected by the Pythagorean theorem. All right, but the idea is now you can do this on some other thing. You could, for instance, write the integral for the ellipse. What tends to be bad in this, unfortunately, is for nasty curves like that ellipse. When you calculate the square root, you get an integral that's too hard to do. So how am I going to calculate the arc length when I can't find the antiderivatives of the thing that comes out? It turns out you get something called an elliptic integral that is actually a non-elementary integral. So it's difficult. There's not a nice formula for it. But even if there's not a nice formula for this, remember, machines can estimate these definite integrals very accurately these days. You get MATLAB or Mathematica or something, it'll estimate these integrals. So even if you can't find a formula for the antiderivative, find the exact arc length, your machine can now estimate it very accurately for you by this formula. So the formula is useful not only for finding nice theoretical results for lengths of curves you can do the integral, but when this thing comes out to be nasty because of the square root, you can still estimate it very, very nicely on the computer. Let's see. I guess I should make one more comment on this. We also define the arc length parameter. So called because people often like to rewrite their parametric curves as a function of this parameter instead of t, right? T is an arbitrary parameter. I don't have to make t the polar angle to go around the circle. I can make it half the polar angle, right? Or the square root of the polar angle or something like that. The arc length parameter is a very popular choice for parameter for a curve C. Again, C of t given by an ordered pair x of t, y of t. T running from wherever, include that goes through t equal t0 interior along the interval, or let's say anywhere on the interval of t values. And again, for a smooth curve, is this, we'll call it s of t, or just s, will be the integral from t0 to t of the square root of dx dt squared plus dy dt squared dt. So that'll define the arc length parameter. You see why it's called an arc length parameter? This is our arc length formula, except instead of going from A to B, we went from a fixed point t0 to an arbitrary point t. And so what does it measure for us? If I'm sweeping out this curve in the plane C, right? I have some point here, x of t0, y of t0. That's a reference point. I can pick any point along the curve I want. And what is this going to be then if I go from t0 to t? I can take an arbitrary point out here, x of t, y of t, and according to formula 2, I'll call this 3, this is now the arc length from here to the arbitrary point t. So this is a function that tells us the arc length going from this reference point t naught, x of t naught, y of t naught, to any point along the curve. It gives you the arc length. Except one little thing. What if t is less than t0? I go from a smaller point to a bigger point. What do I get? Yeah, I get minus the arc length. So what happens is if you go forward, the direction that t is evolving along the curve, it gives you the arc length from here to here. If you go backwards, you get minus the arc length. So it's the arc length parameter, and it tells you how far, plus if you go forward, minus if you go backwards along the curve. A lot of times people like to put t naught at the first point, and then it's just the arc length from the first point, and it's always non-negative, right? Which is kind of convenient. But that'll be the arc length parameter. And then it has this neat property. Its derivative is what? What should be the derivative of that thing? Well, think about it. If by the way, the reason this is called arc length parameter, you can rewrite if s is given as a function of t here, if you can solve this for t as a function of s in reverse, sometimes you can do that, right? If this is some function of t, you can undo it and solve for t as a function of s. If you can do that, you can write x of t of s and y of t of s. And what you've now done is made the curve as a function of arc length s. And so it's like one of those wheels you push off along the ground to measure the track, how far the runners run. The arc length parameter, if you're at any point, s is equal to how far you moved along the curve, just like the wheel tells you how far you moved along the track, right? So it's a convenient thing for rewriting the curve as a function of how far you went as you move along. That's why it's called the arc length parameter frequently. But now ds dt is the rate of change of distance s with respect to time, right? So it's actually your speed. Rate of change, instantaneous rate of change of distance with respect to time makes it the speed. And so we often denote that by v, or v of t. It's just the derivative of the arc length parameter. And what is the derivative? This is an interesting question. What's the derivative of this thing? Second part of the fundamental theorem of calculus, right? Remember seeing this in calculus? If you take the derivative with respect to x of the integral from a to x, a fixed point to x, of f of whatever, tau d tau, the second part of the fundamental theorem of calculus says that this is an antiderivative of f of x. So this just gives you f of x back, right? It's this function plug in the variable endpoint. If you go from a to a variable endpoint, it's an antiderivative of functions whose derivative is this little f, right? You take the antiderivative of the derivative, you get f back. So that's what this is here. This must be the integrand here, just with, it's the square root of dx dt squared plus dy dt squared. So there's the speed. You can measure the speed v of t as this square root. All right, let's see. Not out of time. I was going to do one of these calculations for speed along a curve. Maybe I better wait till next time, I guess. But you can try some of those with this formula. Just calculate speed whenever you need it.